while loops. Near the end of section 2.3, we mentioned that most computational tasks cannot be accomplished using branching programs. Consider, for example, writing a program that asks for the number of x's. You might think about writing something like the following, where we set a variable num(x) equal to the result of taking in whatever the user responds with into the input function, and putting that through the integer function, turning it into an integer, whatever the user types in, creating a variable to print that is just an empty string, and starting all these if-elif checks that will check specifically if this variable num(x) has been set to 1, then it'll print 1x, else if this variable has been set to 2 by the user, then it'll print 2x's, else if it's set to 3, then print 3x's, or rather that it will update the value of this variable to print, and then finally print that variable. But it would quickly become apparent that you would need as many conditionals as there are positive integers, and there are an infinite number of those. Thank you, textbook. What you want to write is a program that looks like the following is pseudocode, not Python. Where it's the same, you start out the same way. You set this variable num(x) equal to what the user passes in to input, and then passing that into the integer function. And the same, you create a variable to print that is an empty string. But then, you arrange the code so that it doesn't have to do a million infinite checks. This is a comment and concatenate x to the variable to print num(x) times. So whatever number gets assigned to this variable will end up controlling how many times x is concatenated to this empty string. That's the suggestion, as it says that's pseudocode. It doesn't actually write out the code itself, it just explains itself. When we want a program to do the same thing many times, we can use iteration. A generic iteration, also called looping mechanism, is shown in the box in figure 2-6. Like a conditional statement, it begins with a test. If the test evaluates to true, the program executes the loop body once, and then goes back to reevaluate the test. This process is repeated until the test evaluates to false, after which control passes to the code following the iteration statement. And this diagram illustrates that. We can write the kind of loop depicted in figure 2-6 using a while statement. Consider the code in figure 2-7. Create a variable x, set it equal to 3. A variable ans, we set equal to 0. A variable num_iterations, which we set equal to 0. And then the while loop. While this condition here in the parenthetical statement remains true, that is that the variable num_iterations is less than the variable x, while that's true, update the value of the variable ans equal to its own current value plus the current value of x. Then, update the value of num_iterations to its current value plus 1. And it will do this, it will execute this code over and over until num_iterations is not less than x. After which, finally, this code will be executed. This f string will be printed, in which replacement fields are included that will be formatted with the current value of x and ans at the time that the code is executed. And as it says, squaring an integer the hard way. The code starts by binding the variable x to the integer 3. It then proceeds to square x by using repetitive addition. The table in figure 2-8 shows the value associated with each variable each time the test at the start of the loop is reached. We constructed the table by hand simulating the code, i.e. we pretended to be a Python interpreter and executed the program using pencil and paper. Using pencil and paper might seem quaint, but it is an excellent way to understand how a program behaves. And if you want to pause and take a look at this, I'm not going to read out this table, it's unnecessary. The fourth time the test is reached, it evaluates to false, and flow of control proceeds to the print statement following the loop. For what values of x will this program terminate? There are three cases to consider. the case in which x equals 0, that in which x is greater than 0, and that in which x is less than 0. Covers everything. Now suppose x is equal to 0. The initial value of num_iterations will also be 0, therefore the loop body will never be executed if it starts out with those values. Suppose x is greater than 0. Then the initial value of num_iterations will be less than x, and the loop body will be executed at least once. Each time the loop body is executed, the value of num_iterations is increased by exactly 1. This means that since num_iterations started out less than x, after some finite number of iterations of the loop, num_iterations will equal x. At this point, the loop test evaluates to false, and control proceeds to the code following the while statement. Now suppose, in case your imagination hasn't been completely drained by all of this, that x is less than 0. Something very bad happens. Control will enter the loop, and each iteration will move num_iterations farther from x rather than closer to it. The program will therefore continue executing the loop forever, or until something else bad, such as an overflow error, occurs. How might we remove this flaw in the program? Changing the test to num_iterations less than the absolute value of x, that is, x passed in as argument to the abs function, almost works. The loop terminates, but it prints a negative value. If the assignment statement inside the loop is changed to ants equals ants plus abs of x, the code works properly. Finger exercise. Replace the comment in the following code with a while loop. Sorry, I keep saying while like that. I don't... No. So we start out this exact same way, creating this variable and this variable. And now it's telling you to try and figure out a way to make this real code with a while loop. Do it. It is sometimes convenient to exit a loop without testing the loop condition. Executing a break statement terminates the loop in which it is contained and transfers control of the code immediately, or control to the code immediately following the loop. For example, the code, explained by this comment here, find a positive integer that is divisible by both 11 and 12. Here we create a variable x, set it equal to 1, start a while loop, and while true, if x modulo 11 is equal to 0 and x modulo 12 is equal to 0, break, you're done. If not, though, it'll go on and execute this x, where you update the value of the variable x equal to its own current value plus 1. Finally, once this is done, print that variable x, followed by the string is divisible by 11 and 12. So this will just keep on searching through, adding one at a time, the numbers starting at 1, until it finds something that is divisible by both 11 and 12. That is, that it can be divided by 11 and 12 with a remainder of 0. And finally, this would result in it printing 132 is divisible by 11 and 12. If a break statement is executed inside a nested loop, a loop inside another loop, the break will terminate the inner loop. Finger exercise. Write a program that asks the user to input 10 integers and then prints the largest odd number that was entered. If no odd number was entered, it should print a message to that effect. Do it. I'm not going to do it. For loops and range. The while loops we have used so far are highly stylized, often iterating over a sequence of integers. Python provides a language mechanism, the for loop, that can be used to simplify programs containing this kind of iteration. The general form of a for statement is, and recall that the words in italics are descriptions of what can appear, not actual code. For variable in sequence code block. The variable following 4 is bound to the first value in the sequence, and the code block is executed. The variable is then assigned the second value in the sequence, and the code block is executed again. This process continues until the sequence is exhausted or a break statement is executed within the code block. For example, the code variable total set equal to 0, and then this for loop for num in 77, comma, space 11, comma, space 3, and we'll get to that. Update the value of the variable total equal to its own current value plus the current value of num, the index variable of the for loop. And then print, finally, that variable. And this will print 91. The expression 77, comma, space 11, comma, space 3 in the soft round hug of parentheses is a tuple. We discussed tuples in detail in section 5. For now, just think of a tuple as a sequence of values. The sequence of values bound to variable is most commonly generated using the built-in function range, which returns a series of integers. The range function takes 3 integer arguments, at least it can go up to 3. Start, stop, and step. It produces the progression start, then start plus the value of step, then start plus the value of step multiplied by 2, etc. If step is positive, the last element is the largest integer, such that start plus I times step is strictly less than stop. If step is negative, the last element is the smallest integer, such that start plus I times step is greater than stop. For example, the expression range 5, 40, 10 yields the sequence 5, 15, 25, 35, because it starts at 5 inclusive, it goes up to but excludes the stop number, 40, and it does so in increments of 10. So it's 5, 15, 25, 35, end. And the expression range 40, 5, negative 10 yields the sequence 40, 30, 20, 10. Starts at 40 inclusive, goes up to but does not include 5, and it does so in increments of negative 10, 10 steps backwards at a time, as it were. If the first argument to range is omitted, it defaults to 0, and if the last argument, the step size, is omitted, it defaults to 1. So you can call the range function with just one argument, and that's the end point if you just give it 1. For example, range 0, space 3 and range 3 both produce the exact same sequence, 0, 1, 2. The numbers in the progression are generated on an as-needed basis, so even expressions such as range 1 million consume little memory. We will discuss range in more depth in section 5.2. Consider the code. X set equal to 4, then for I in range x, print I. The value of our variable x being 4, and this is just like calling if we called the range function with 4 as one argument, meaning it will go up to but not include that number. So this would print 0, 1, 2, 3. The code in figure 2-9 re-implements the algorithm in figure 2-7 for squaring an integer, corrected so that it works for negative numbers. Notice that unlike the while loop implementation, the number of iterations is not controlled by an explicit test, and the index variable num_iterations is not explicitly incremented. Here we've got x equal to 3, we got zans equal to 0, and we got a for loop for num iterations in range, the absolute value of x, update the value of our variable ints equal to its own current value plus the value of passing in, or the result of passing in x to the absolute function. Then finally, once that's completed, print this f string, which is just like before with this replacement field. Notice that the code in figure 2-9 does not change the value of num iterations within the body of the for loop. This is typical, but not necessary. Which raises the question of what happens if the index variable is modified within the for loop. Consider. For I in range 2, print I and update I to 0, then print I again, all within the body of the for loop. What do you think? Do you think that it will print 0, 0, 1, 0, and then halt? Or do you think it will print 0 over and over again? Well, the answer is 0, 0, 1, 0. Before the first iteration of the for loop, the range function is evaluated, and the first value in the sequence it yields is assigned to the index variable I. And just note, again, that this I, calling it I is just sort of a convention, and you could call it Jim, you could call it Jam. If it's more descriptive to call it something else, more in context, call it that. Don't call it I, but remember that it's not a specific keyword or something. You call the index variable whatever you want, and it's created whenever you make the for loop or other things, At the start of each subsequent iteration of the loop, I is assigned the next value in the sequence. When the sequence is exhausted, the loop terminates. The above for loop is equivalent to the code where we set an explicit index, a variable called index, to 0. We set a variable called last index to 1, then a while index is less than or equal to last index. So starting out, this is the case, so this will run. Update the value of I, the actual index variable, to be equal to the variable that we called index. That's confusing. Then print I. Then update the value of I to 0. Then print I again. Then update the value of index to its own current value plus 1. Now, notice, by the way, the code with the while loop is considerably more cumbersome than the for loop. The for loop is a convenient linguistic mechanism. Now what do you think? X set equal to 1, for I in range X, print I, and update the value of the variable X equal to 4. What do you think it prints? Just 0, because the arguments to the range function in the line with 4 are evaluated just before the first iteration of the loop and not reevaluated for subsequent iterations. Okay? If there's something in the body of the for loop, it could be updated, but basically whatever value X happens to be whenever the interpreter reaches this line, that's what it's going to do in here. It's not going to, whatever is then later done to X in the body of the for loop makes no difference. Now, let's see how often things are evaluated when we nest loops. Consider. This guy says consider a lot. X equals 4, a set variable X equal to 4. Start a for loop for j in range X, and a nested for loop for I in range X. Update the value of the variable X to 2. Now how many times is each of the two loops executed? We already saw that the range X controlling the outer loop is evaluated the first time it is reached, and not re-evaluated for each iteration. So there are 4 iterations of the outer loop. That implies that the inner for loop is reached 4 times. The first time it is reached, the variable X is equal to 4, so there will be 4 iterations. However, the next 3 times it is reached, X equals 2. So there will be 2 iterations each time. Consequently, if you run this code, which first defines X as equal to the integer 3, and then for j in range X, print the string iteration of outer loop, and then a nested for loop for I in range X, print the string iteration of inner loop, finally update the value of X to 2. This will illustrate for us like an injection of radioactive material to see somebody's circulatory system exactly how these loops are executing. They would get 1 iteration of outer loop, 3 of the inner, 1 more of the outer, 2 of the inner, 1 more of the outer, 2 final of the inner. The for statement can be used in conjunction with the in operator to conveniently iterate over characters of a string. For example, say we have a variable total set equal to 0. The for loop for c in, you see how? You can call it anything. It don't even matter. For c in this string, not an integer, note, or c in this string 1, 2, 3, 4, 5, 6, 7, 8, set the value of the variable total equal to its current value plus the value of turning the index variable into an integer. That is for c, so this would iterate over all of the characters in this string, right? And at each step of the way, at each iteration of the loop, c will equal a new character, because it's like a karaoke ball hopping from word to word. Okay, in the first iteration it will be equal to 1, in the second iteration c will be equal to 2, in the third iteration it will be equal to 3, etc. And for each new iteration, this new value is what is passed in to the integer function here, thus allowing this to create a range of different values for total, right? This code would sum the digits in the string denoted by the literal 1, 2, 3, 4, 5, 6, 7, 8, and prints the total. Finger exercise. Write a program that prints the sum of the prime numbers greater than 2 and less than 1000. I can't indicate that with my hands. And you probably want to use a for loop that is a primality test nested inside a for loop that iterates over the odd integers between 3 and 999. Yeah, that's exactly what I was thinking. That's what I want to do for sure. Style matters. Much of this book is devoted to helping you learn a programming language. But knowing a language and knowing how to use a language well are two different things, by God. Consider the following 2 sentences. Everybody knows that if a man is unmarried and has a lot of money, he needs to get married. Versus the opening line, any Jane Austen fans out here, it is a truth universally acknowledged that a single man in possession of a good fortune must be in want of a wife. Each is a proper English sentence, and each means approximately the same thing, but they are not equally compelling and perhaps not equally easy to understand. Just as style matters when writing in English, style matters when writing in Python. However, while having a distinctive voice might be an asset for a novelist, it is not an asset for a programmer. The less time readers of a program have to spend thinking about things irrelevant to the meaning of the code, the better. That's why good programmers follow coding conventions designed to make programs easy to understand rather than fun to read. When it comes down to it, I mean, if you're just programming for yourself and not in a company, like, make it weird as hell. Yeah, it's for universe. Most Python programmers follow the conventions laid out in the PEP 8 style guide. Like all sets of conventions, some of its prescriptions are arbitrary. For example, it prescribes using 4 spaces for indents. Why 4 spaces and not 3 or 5? No particularly good reason. But if everybody uses the same number of spaces, it is easier to read and perhaps combine code written by different people. More generally, if everyone uses the same set of conventions when writing Python, readers can concentrate on understanding the semantics of the code, rather than wasting mental cycles assimilating stylistic decisions. The most important conventions have to do with naming. We have already discussed the importance of using variable names that convey the meaning of the variable. Noun phrases work well for this. For example, we used the name num_iterations for a variable denoting the number of iterations. When a name includes multiple words, the convention in Python is to use an underscore to separate the words. Again, this convention is arbitrary. Some programmers prefer to use what is often called camel case, e.g., like this, where everything is lowercase until the second word, and beyond that each word starts with in title case, right? arguing that it is faster to type and uses less space and, gives it. There are also some conventions for single character variable names. The most important is to avoid using a lowercase l or uppercase I, which are easily confused with the number 1, or an uppercase 0, which is easily confused, or an uppercase O, which is easily confused with the number 0. That wasn't even intentional. That's enough about conventions for now, boy. We will return to the topic as we introduce various aspects of Python. We have now covered pretty much everything about Python that you need to know to start writing interesting programs that deal with numbers and strings. In the next chapter, we take a short break from learning Python and use what you have already learned to solve some simple problems. Let's go over the terms real quick. See if you can remember the meaning of all of these terms. Low-level language, high-level language, interpreted language, compiled language, source code, machine code, Python. Integrated development environment, Anaconda, Spider, IPython console, shell, program, script, command, statement, object, type, scalar object, non-scalar object, literal, floating point, bool, none, operator, expression, value, shell prompt, variable, binding, assignment, reserved word, comment, encode, straight line program, branching program, conditional, indentation in Python, nested statement, compound expression, constant time, computational complexity, conditional expression, strings, overloaded operator, repetition operator, type checking, indexing, slicing, type conversion, casting, formatted string expression, input, Unicode, iteration, looping, pseudocode, while loop, hand simulation, break, for loop, tuple, range, in operator, epbait, style guide. Lecture 3 reading done.